This is Appendix C, page 2. Let's go to the definition of a vertical line test. If every vertical line intersects the graph of a relation in no more than one point, then the relation is a function. So let me give you two examples. The first one is a curve that is a function. And we can see that this is a function because no matter where I draw a vertical line, do you see how it passes through this function in just one point? So this is a function. Another example, let's draw a circle, and this is not a function, and the reason why is, do you see how you could draw a vertical line that passes through the graph in more than one point? So this is not a function. So if you can draw any vertical line that passes through the graph in more than one point, then it's not a function. Example 4. Now we want to use the vertical line test to determine whether the relations graphed in example 3 are functions or not. So let's go to example 3. So the first one, example 3a, if we draw a vertical line through these 2 points, do you see how it passes through the relation in more than one point? So this is not a function. I'll go ahead and just write that here, and then you can write it on the next page yourselves. For part B, no matter where I draw a vertical line, do you see how it only passes through the graph at one point? So this is a function. Part C, I can draw a vertical line through this graph at more than one point, and so this is not a function. And then part D, even though the curve is very steep, no matter where I draw a vertical line, it only passes the graph at one point, and so this is a function. So that was example 4. So I'll just write here to see example 3 since we just wrote those there. Example 5, determine whether each relation defines y as a function of x and then give the domain and range. For these examples, we're going to write them in equation form. The first one, if we have y is equal to 2x minus 5, is this a function? Well, for each x, so no matter what number you plug into x, do you see how you're just going to multiply that number by 2 and then subtract 5? So that means that yes, it is a function. For the domain, do you see how you could plug any real number in for x? And so to show that, we just go from a negative infinity to positive infinity. And for any number multiplied by 2, subtracting 5, you're going to get an output that it could be any real number, and so this is all real numbers also for the range. So remember, the domain is the set of all x values, and the range is the set of all y values. Part B, we have y is equal to x squared plus 3. To determine if it's a function, if we take some number for x and square it, and then add 3, we're just going to get one specific number for y, and so this is a function. The domain is the set of all x values. X could be any number, because we can square any number. And if you square a number and then add 3, now this is a little tricky, because if you square a negative number, do you see how you're going to get a positive number? So what is the lowest value that you could have for x squared? Well, the lowest value you can have for x squared is 0. And so if we take 0 squared, that's 0, plus 3 is 3. So the lowest y value that we're going to have for this one is 3. And that includes the 3, so we have a bracket. If you're not sure, you could always draw a graph of it. And I'll go ahead and do that here also, just so you can see what it looks like. We'll be graphing more in the next section, but if we graph this, you could plot points. You'll see that this ends up looking like a parabola where the lowest point is at 0, 3. So looking at the range from bottom to top, you can see the lowest y value is 3, and then it keeps on going up. For part C, the equation is x is equal to the absolute value of y. Now this one, do you see how you could have two different y values for the same x? So an example would be with x is 3, do you see how y could be 3 or negative 3? We could also write this as y is equal to positive or negative x if we think of the definition of the absolute value sign. So these two equations mean the same thing. And this is for x greater than or equal to 0. Because here, do you see how x has to be greater than 0? You're finding the absolute value, or it could be equal to it if y is 0. Is this a function? Well, we just saw that with the example that it's not. So I will just write out a little example here for you. If we have a table and we plug in 3 for x, you see how y could be 3 or it could be negative 3. So this is not a function. All you need to do is find one example to show that it's not a function. The domain is the set of all x values. And do you see here how the lowest x value is going to be 0 because we're taking the absolute value of numbers to give you x? So this is going to be from 0 to infinity, and that includes the 0. But for the range, you can take the absolute value of any real number. So this is from negative infinity to positive infinity. And if you'd like to see the graph to get a better understanding of this, you could plot points, and you'll see that it is an absolute value equation. Is like a V-shaped, but it's turned on its side. D, y is equal to 3 over x plus 2. This is called a rational equation because it has a fraction in it. Is this a function? Well, for each x, no matter what number you plug in for x, do you see how you're just going to get one specific y? So this is a function. And then to determine the domain, that's the set of all x values. Can you see how there's one number that x cannot be, because that would make this fraction undefined? So the domain, x cannot be negative 2. So we could write this as x, so any x such that x is not negative 2, because that would make the denominator 0. Or if you'd rather write it in interval notation, you go from negative infinity to negative 2, but don't include it. Or negative 2 to infinity. And then the range is a little tricky. Do you see how the numerator will never be 0? If the numerator never can be 0, then that means that this whole fraction can never be 0. And so the range is the set of all y, but y cannot be 0. And again, we can write this in interval notation, just showing that it could be any number except for 0. And then the next part of the section deals with function notation. So that's how we write functions. If you remember that function notation, y equals f of x means f evaluated x, not f times x. So f of x is just another name for y. So for example 6, here we're given two functions, and the first one's quadratic. F of x is quadratic, g of x is linear. We want to find f of negative 3. So we're going to plug in negative 3 for the x's in the f function. We have to be very careful because there's a negative in front of that x squared. And then we simplify. If we square the negative 3, we get 9, but we still need to bring that negative down. 2 negatives multiply to give us a positive. And now we can simplify. So we have 9 plus 4 is 13. So if the input is negative 3, then the output is 13. Another one. Let's plug in r for x. So we have negative r squared minus 6r plus 4. There's nothing we can do to simplify this expression, so all of this is the output if the input. For part C, we have g of r plus 2. I'm going to plug in r plus 2 for x. So we have 3 times the quantity r plus 2 plus 1. To simplify this, we distribute the 3 and then combine like terms. So if the input of g is r plus 2, then the output is 3r plus 7.